Welcome to the Picture Language Seminar. We're very happy today to have Patrick Coles. We had to postpone his seminar scheduled earlier, but wonderful that he can be with us today. And actually, it's the last of our regular weekly seminars before a summer break. But next, in a couple of weeks, from June 20 to 23rd, we're going to have a meeting in Cambridge, Massachusetts, who, if you're close enough to come, you're welcome to come to the talks. And we're going to have some familiar faces there and perhaps some unfamiliar ones, bringing together ideas from a broad spectrum of mathematics, physics, quantum information related to quantum computing. So without further ado, I'd like to introduce Patrick, who's expert on machine learning, Barren Plateaus, and he's going to tell us about training landscapes for parameterized quantum circuits. So Patrick, why don't you share your screen?
Okay. Oops. Okay. Can you see my slides?
Absolutely, yes.
Okay, great. So thank you so much for this very kind invitation. It's definitely an honor to be talking here. And so today I'll be talking about training landscapes for parameterized quantum circuits. And I want to give a little bit of background for why this is interesting. This is a paradigm for, oops, it's not good. Let's see. There we go. Okay. A paradigm for various fields of quantum physics. One is quantum machine learning, which I'll talk about, and another is variational quantum algorithms, and then finally quantum optimal control. And in each of these, in each of these fields, you have an input state, and then a parameterized unitary. Of course, a unitary is like a time evolution. And then you have a final state, psi of theta. And so in all of these fields, they all use parameterized unitaries. And then they want to train the parameters theta and to achieve some task. And so so this is a common paradigm. And just to give an example, in quantum machine learning, the idea is that you have a data set. It could be a classical data set, like cats, pictures of cats and pictures of dogs. And then you want to distinguish those, those pictures or classify pictures. Or it could be a quantum data set, in which case you would have, say, different quantum states associated with, for example, different phases of quantum matter. And you would want to classify those states as being part of one phase or another phase. And then you would pass those into what people might call a quantum neural network, which is basically just a quantum circuit that's parameterized. And then you would train that in order to do the classification. So I just want to sort of show you the application for what people would call quantum machine learning, where you use a quantum circuit as your quantum neural network to classify different data sets. The other paradigm that I mentioned was variational quantum algorithms. And in that paradigm, I like to think of it as automated programming of quantum computers. So there's sort of the old school set of algorithms that you see in textbooks, like Nielsen and Schwang's textbook, like Shor's algorithm for factoring. There's also algorithms for solving linear systems of equations. There's various types of textbook algorithms that you'll find that you can try to put on a quantum computer. But for today's quantum computer, these algorithms essentially just don't fit on today's quantum computers, and they don't fit in two different ways. They don't fit in terms of numbers of qubits that they require, but they also don't fit in terms of the circuit depth that they require. So both in terms of width and depth of the circuit, they're too big for today's quantum computers. And but we do have quantum computers that are on the order of 100 qubits in size, courtesy of IBM and Google and other companies. And so the question is, can we make use of these quantum computers that are now commercially available? And people have come up with this sort of paradigm that I'm showing here, which could be used to sort of automatically program quantum computers variationally. And the idea is that you would have some input state, rho, here I show, and then a quantum circuit that's parameterized, has some parameters. You can think of this as just u of theta, so a unitary that depends on some parameters theta. Some people call that an ansatz for the solution. And then you have a measurement at the end, and you use the measurement to define a cost function. And the cost function is going to determine what your task is. So your task might be, for example, to find the ground state of a certain Hamiltonian, in which case the cost function would just be the energy, the expectation value of the energy under that Hamiltonian. And then your goal would be to minimize that cost function. And so then you have a classical optimizer, which then updates the parameters of your circuit in order to reduce the value of that cost function. And then you do a feedback loop where you do this many times in order to try to minimize that cost function and hence accomplish this task. And but it's a very flexible paradigm. For one, the idea is that you can imagine being very frugal with the circuit depth and the number of qubits that you use. And so you can so the idea would be to, all right, given my limited resources that I have with today's quantum computers, both in terms of circuit depth and numbers of qubits, how can I approximately solve the problem that I'm trying to solve? So this paradigm, has been applied to many different applications. I mentioned the case of, say, finding the ground state of a Hamiltonian. That obviously has applications for electronic and nuclear structure. So if you're interested in, say, finding the ground state of a molecule or finding the ground state of a nucleus of an atom, then you can use this what's called the variational quantum eigensolver in order to minimize the energy and find an approximate ground state. We also have been pushing the frontiers of applying this same technique to dynamical simulation. And I won't go into the details there, but it turns out that if you want to dynamically simulate a system, then the standard method is often called Charterization, where the circuit depth grows with the problem size in proportion. The circuit depth grows with the time that you want to simulate for. But that's an issue, of course, for it generates deep circuits. And so, we've tried to variationally learn circuits that don't go very deep by learning approximate diagonalizations of the time dynamics. Combinatorial optimization is another application. This is often called the quantum approximate optimization algorithm. And there, the idea is that there's certain combinatorial optimization problems that often are cast as like graph problems. So for example, max cut, we tried to find the cut through a graph that maximizes the number of edges that the cut passes through. Then people can recast that as a Hamiltonian ground state problem. And so then it kind of falls into the same category as finding Hamiltonian ground states variationally. And then finally, another problem that our group has worked on is solving linear systems of equations. So AX equals B, and you want to solve for X. And I can try to elaborate a little bit more on that last application, just as an example to show you of a variational quantum algorithm that we've developed. So this, we called it the variational quantum linear solver. And the idea is that you want to solve, so the standard linear systems of equations, ax equals b, you want to solve for x. In practice, the sort of quantum version of that is that you want to prepare a quantum state x such that it's proportional to the solution. Because of course, x has to be normalized if it's a quantum state. And so, so the idea is you want to prepare x such that ax is proportional to b. And so you could ask, like, all right, well, what kind of cost function would you use in that case? Well, you could use a cost function that penalizes you whenever ax has a component orthogonal to b. You want ax to be essentially parallel to b. And so if ax happens to have any component orthogonal to b, then you could penalize yourself for that. And hence, your cost function can just sort of quantify like the norm of the component of ax that's orthogonal to b. And so, so that's indeed what we use as our cost function here. And we use, and then we can have a gate sequence v of alpha here that that is parameterized in order to prepare an approximate solution x of alpha. In this particular algorithm, we assume that the matrix A is given to us in a certain form so that we can actually kind of implement A on a quantum computer. And for that, we had to assume that A is given to us as a linear combination of unitaries. And then if A is given to us in that form, then we can actually implement A effectively on a quantum computer. And then we also assume that we're given the unitary U that prepares the state B. So once again, we have to be able to implement sort of the preparation of B on a quantum computer. But if these two things are given to us in kind of this quantum form, then we can compute our cost function efficiently on a quantum computer, and hence do this sort of back and forth minimization where we compute how much component ax has orthogonal to b, and then adjust the parameters, and then keep going back and forth and try to minimize our cost function. So I just wanted to give you that as an example of how you can use this variational quantum algorithm paradigm, to sort of automatically generate algorithms to solve problems that you might be interested in. For the remainder of my talk, I want to focus on the question of, scalability. So, will these variational quantum algorithms scale well? And that's the key question, because ultimately they're heuristic algorithms. And so we don't always have, or we typically don't have analytical proofs that they scale well, in contrast to the textbook algorithms that you see in quantum information textbooks like Shor's algorithm. And so, of course, numerical heuristics will play a role in this. And just as an example, we've looked at how you can consider linear systems problems that have the problem size as a free parameter, and you can vary the problem size. Just as an example, we looked at the time to solution for our problem for an Ising model kind of linear system, where the number of spins is a free parameter. And in this case, we saw linear scaling with a number of qubits, which is encouraging because classically you would expect to have exponential scaling with the number of qubits. In other words, that's polynomial scaling with the matrix dimension. So, at least with this simple example, it's encouraging that you might see an exponential speed up. And we also considered—
Excuse me, Patrick, could you just tell us what is kappa?
Kappa is the condition number of the matrix. So the condition number of the matrix A. So it's a condition number of the matrix A in the system AX equals B. So that is the ratio of the largest singular value to the smallest singular value of the matrix A. So there's the idea is that if the condition number is high, then it's harder to invert A, because the idea is that it's the idea. Well, if the condition number is infinite, then it's like not an invertible matrix, right? Because it has some eigenvalues that are 0. But the idea is that it's typically harder to invert matrices that have a large condition number. And so then as kappa gets larger, the problem is harder to solve, is the idea. So solving for A inverse B, right? And so the difficulty of the problem grows with kappa, the ratio of the largest to the smallest singular values of A. And anyway, we also looked at random sparse problems where we just considered sparse matrices when A is a sparse matrix, and we also found power law scaling in that case, which is also indicative of a possible exponential speed up over classical algorithms, which would have exponential scaling with the number of qubits. So these are just heuristics, though, and there's always the critique in the back of your head, which is that these are specific problems and not necessarily the most general kind of problems you might be interested in, and it's not a proof. And so what we've tried to focus on in our work is not just doing numerical heuristics, but also looking at what can we learn analytically about these algorithms. And if you're trying to identify sources of scaling and efficiency in this paradigm, you might say, well, one source of inefficiency could be how much circuit depth you need to reach a good approximation of a good solution that solves the problem. And maybe it turns out that with small circuit depth, you can't find good solutions to your problem. Another question you might ask is, how many shots do you need? How many repetitions of this circuit do you need in order to estimate your cost function or the gradient of your cost function in order to train your parameters? Maybe it turns out that you need a lot of shots in order to estimate your cost function. And then finally, you could ask how many iterations you need to find the global optimum. Maybe it turns out that you have a landscape that's very bumpy and you have a lot of local minima, so it's not very convex. And so you worry that you might need a lot of iterations in order to find the global optimum. And so there's several sources of scaling and efficiency that you might encounter in this paradigm. And there has been work on each of these issues. And our work, there has been work identifying that, for example, for highly correlated systems that you might be interested in, like high temperature superconductors, for example, and you want to find the ground state of that system, there are some, like you often need deep circuits in order to prepare such ground states and to distinguish them from, say, low-lying excited states. So there are some issues there, especially for highly correlated systems in terms of the circuit depth. There's also issues with local minima, as I said, in terms of the number of iterations you need to find the global optimum. And finally, what our work is focused on is the number of shots needed to estimate the cost function or the gradient of the cost function. And that's where our work on so-called Barren plateaus, which I'll define later, has been on. And so that's kind of the focus of my talk, which is studying this Barren plateau phenomenon, which is really getting into understanding the shape of the landscape of for when you try to train the parameters. And so just from like a physicist perspective or an empiricist perspective, you could just sort of try to do this and see what happens, and see empirically or phenomenologically what you observe. And for some problems, what you find out is that if you plot the total number of shots that you need to start training your cost function versus the number of qubits, so the y-axis here is the number of shots that you need to begin the training process. So imagine that your cost function starts at some large constant value, like a value of 1, and then you want to reduce the cost function to say 0.9. So you want to begin the training process, and you could plot the number of shots that you need, shots meaning the number of repetitions of your quantum circuit, versus the problem size, so the number of qubits, which is on the x-axis. And what we find is that regardless of whether we have a gradient-free optimizer like Nelder, Mead, Powell, or Korbila, or a gradient-based optimizer like gradient descent, we see that the number of shots in certain cases grows exponentially with the number of qubits. The number of shots that you need to start training grows exponentially with the number of qubits. So notice that the y-axis here is on a log scale. So, so we're seeing in many cases exponential growth in the number of shots needed to start the training process. That's obviously bad because the whole goal of quantum algorithms is to avoid exponential scaling, right? We want polynomial scaling to try to get that exponential speed up over classical algorithms. And so we saw this phenomenon, and other groups have seen it as well. And we were wondering, why does this happen and how do we prevent it? And so in order to understand why that's happening, why we see exponential growth in the number of shots needed, we need to understand the landscape of the training landscape. So when we plot sort of the cost function versus the parameter values. And so I want to delve into the details of trying to understand the shape of the cost function landscape. And the first paper to really do this analytically was by the Google group. They had this paper called Barren, Plateaus, and Quantum Neural Network Training Landscapes from a couple years ago. And they considered the following setting. They imagined taking your ansatz or your parameterized unitary, and they broke it up into 3 pieces. One piece is the part that you're interested in studying the partial derivative of. So theta sub k, maybe you're interested in the partial derivative of the cost function with respect to theta sub k. And then you can consider the unitary prior to that, which is called u minus, and the unitary after that, which they called u plus. And then they wanted to understand the partial derivative with respect to theta sub k and how that scales with the problem size. And what they computed the variance of that partial derivative, and they got this formula for 3 different scenarios. One scenario is whenever the unitary to the left, u minus, forms what's called a 2 design. The other scenario is when the unitary to the right forms a 2 design. And the final scenario is whenever both form a 2 design. And so just to remind you, what is a 2 design? Well, a T design is a set of unitaries that reproduces averages over the whole unitary group up to the Tth order. And so a 2 design would be a set of unitaries. It could be a discrete set or it could be a continuous set. But the idea is that it's a set of unitaries. Here I show the case where it's a discrete set. And this is the average over the unitary group, the whole unitary group on the right-hand side here. But it's a set of unitaries that reproduces averages over the whole unitary group up to the Tth order. And so a 2 design would be something that reproduces averages, 2nd order averages over the unitary group. So you might say, okay, well, that's some abstract idea, but I'll give you an example on the next slide of what of an example of something that's a 2 design. Anyway, so they found that whenever u minus forms a 2 design, they get this top expression, and you'll notice that there's this exponent in the denominator, 2 to the 2n. And similarly, if u plus forms a 2 design, and then also if both form the 2 design, in all cases they find this exponent in the denominator, which is like 2 to the power of n. And so if you were to just kind of look at the scaling, the idea is that if u plus or u minus forms a 2 design, then the variance of the partial derivative is exponentially vanishing in number of qubits. Now, the first moment of the partial derivative is 0, because the idea is that the partial derivative is sort of centered about 0. And so if the variance is exponentially vanishing, what that means is that the partial derivative is concentrating exponentially around the value of 0 as you increase the problem size. That's obviously bad, and that's what people call the Barren Plateau phenomenon, because it means that all your partial derivatives are exponentially small, and hence your landscape looks like it has a barren plateau. This would be kind of what it would look like. So the idea is that the vast majority of the landscape is very flat. There might be some very small region of parameter space in which you have a large gradient, but that's a very small, it turns out you can show that it's actually exponentially small region of parameter space. The vast majority of parameter space has this very small gradient, which is what is known as the Barren Plateau. Now, going back to the question of what's a 2 design, are there examples of 2 designs that are practically relevant? It's been shown actually that this kind of structure where you have local gates, and with this brick-like structure, actually forms a 2 design whenever the circuit depth is polynomially growing in the number of qubits. And this is actually of interest to people who design quantum computers like Google and IBM, because this is what people would call a hardware efficient ansatz, because the ansatz's connectivity matches the connectivity of the device that they've built. So the sort of superconducting quantum computers that IBM and Google have typically have either 1-dimensional or 2-dimensional locality. For example, they just have like a 2-dimensional grid. And so it's very natural to have 2-dimensional local gates there, and built in this kind of fashion. So this is very useful because this kind of ansatz matches the connectivity of real hardware. But it turns out that such hardware efficient ansatzes form a 2 design whenever the circuit depth grows polynomially in the number of qubits. And hence this sort of very practically relevant ansatz also would have a barren plateau in the training landscape. And so this, whenever its depth grows polynomially in the number of qubits. And hence this result was actually very important because it made people realize that the sort of circuit that they wanted to use for their device was potentially untrainable at large scale.
Can I ask a question about this?
Yeah.
Thanks. This is Will Kirby. So the question is, which of these gates need to have parameters in order for that to be true? Does that true if all of these gates have parameters, or some subset?
Yeah. So well, yeah. I was thinking of each gate having a parameter in this case, and yeah, there's also questions of what happens whenever you correlate parameters. So I was thinking of each gate having an independent parameter from each other gate. Mm-hmm. And it turns out that if you do correlate parameters, you can actually get larger gradients and potentially even avoid barren plateaus, like if you tie parameters together.
Right. Okay.
Of course, that dramatically reduces the expressivity of the ansatz, but nevertheless, that is a way to try to avoid such things. But I was thinking of a scenario where each gate was parameterized and it was parameterized independently of each other gate.
Yeah. Okay. Thanks.
Yeah. Mm-hmm. So, yeah. So that's like the original Barren Plateau phenomenon as it was discovered by the Google group, and now we can sort of go back and understand that phenomenology that I showed you before of the total number of shots growing exponentially with the number of qubits, because the idea is that exponential precision is required to escape the Barren Plateau. So if you just randomly initialize the parameters of your circuit. So imagine that circuit that we just showed on the previous slide, and then you randomly pick the parameters of that circuit. The idea is that with very, very high probability, you'll be sitting on the Barren Plateau and not in the valley containing the global minimum. So then if you want to sort of escape that Barren Plateau and move into that valley containing the global minimum, it requires exponential precision to escape that. And so you need very, very high precision on that gradient, which is so small, in order to figure out where to go. So that's why it's taking so many shots in order to start the training process. So shots are obviously associated with the precision that you get. So more shots means more precision. So, and then, what's interesting, like naively, some people thought that this would just affect gradient-based optimizers, because after all, the proof is that the gradient shrinks exponentially with the number of qubits. That's the direct, so the direct implication is that gradient-based optimizers are going to suffer from this. But it turns out that it's not just gradient-based optimizers that suffer from this, because you can show that, it's cost function differences on average will also be exponentially suppressed. So this little proposition here is basically stating that if you look at the difference, if you sort of pick 2 points on the parameter landscape at random, then chances are the difference in their cost values will be exponentially small as well. And gradient-free optimizers like Neld or Mead use cost function differences as a means for making their decisions for how to update the parameter values. So they would have one, say a set of points, and they would look to see which point has the lowest cost function value. And then based on that, they would proceed how to update the parameters. And so gradient-free optimizers also suffer from this Barren Plateau phenomenon as well. And they also require exponential shot cost too. And then hence why we see that numerically. And then, so you might also say like, well, what if we consider higher order derivatives like the Hessian? Some people have proposed using Hessian-based optimizers. But those two, as you might suspect, I mean, intuitively, you would probably suspect this, but you can show that, the Hessian magnitude is basically upper bounded by the variance of the partial derivatives. So higher order derivatives, can effectively be bounded by the first order derivatives. And so both the Hessian as well as derivatives even higher in order are also exponentially suppressed. And so, regardless of whether you use a gradient-free optimizer or a gradient-based or higher order derivative-based optimizer, it appears that changing the optimizer doesn't solve the exponential scaling. So it looks like this Barren Plateau phenomenon is kind of a deep issue. It's not just related to what optimizer you choose. It looks like a complexity theoretic issue that's non-trivial to solve. Yeah, so any questions on what I've talked about thus far? Yeah. If not, I'm going to move on to the next question, which is, where do Barren Plateaus come from? So I've sort of presented to you the phenomenology of Barren Plateaus. And you might say, well, what is the mechanism by which Barren Plateaus arise? And I sort of alluded to this already, but it comes from highly expressive ansatzes that have a high expressivity. Conversely, you can think of expressivity as a reflection of how much knowledge you have. If you have an ansatz that's highly expressive, then that means you have a lot of ignorance about the solution to the problem. It's sort of a reflective of a lack of knowledge of the solution. And so we had this paper that was called Connecting Ansatz Expressibility to Gradient Magnitudes in Barren Plateaus. And there we considered, basically, we used a measure of expressivity that was introduced by Alamos Biraguzik's group. And, this measure, well, they have one measure that's based on, the input state, and the other is based on the sort of measurement operator. So you can sort of quantify expressivity based on sort of moving forwards in time or moving backwards in time. But in any case, we use their measure of expressivity, which basically quantifies how much of the unitary group your ansatz is covering. So this picture on the left-hand side shows two cases, one in which you have a low expressivity, so where maybe you cover some fraction of the unitary group, so you cover some potential solutions, but not other potential solutions. And so, and then there's another scenario where you have a high expressivity, so your ansatz can cover a very large fraction of the unitary group. You can imagine that you might like the second scenario because you could potentially reach better solutions if you can cover the whole unitary group, whereas in the first case, you're sort of missing some solutions. And so, initially people thought, well, high expressivity could be good. But as we showed in our work, it turns out there's a connection between expressivity and these barren plateaus appearing in your landscape. And so we considered this standard cost function that shows up in the variational quantum eigensolver, where you're basically just looking at the energy of your state under a certain Hamiltonian. And like I said, we considered this expressibility measure. And then we're able to show as our main result that the variance of the partial derivative of a certain parameter in the ansatz is upper bounded by a sum of two terms. One of the terms has this 2 to the 2n in the denominator, and this term is very, very closely related to the term that appears in the Google result that I showed you earlier. This is an exponentially vanishing term. And then we have a sort of fudge factor that quantifies or captures the expressivity of your ansatz. And the idea is that whenever your expressibility of your ansatz approaches that of a 2 design, this fudge factor disappears, and then we recover that the variance is upper bounded by an exponentially vanishing cost function, an exponentially vanishing term, excuse me, and hence this generalizes the Google result to approximate 2 design. So we recover the Google result whenever your ansatz forms a 2 design, but then we can sort of move away from that to approximate 2 designs. So it's just sort of intuitively capturing the fact that even if you don't have an exact 2 design, if you have something that's approximately a 2 design, then your partial derivative can be bounded by a function that's approximately exponentially vanishing. So and so we make this sort of quantitative connection between gradient magnitudes and the expressivity of your ansatz. And so then that naturally leads you from a design perspective to the question of, well, how do I reduce the expressivity of my ansatz? Because obviously we don't want ansatzes that are so expressive that they form a 2 design. And so, the first thing you might consider is reducing the circuit depth. And indeed, you can show that as you reduce the circuit depth, the gradient magnitudes get higher and higher. So here on the y-axis, I'm basically plotting the magnitudes of the partial derivatives or their variance versus the number of qubits. The red curve corresponds to a deep circuit where you basically are forming a 2 design, and hence we see this nice exponentially vanishing curve. But then if you reduce the circuit depth, then you're moving away from the 2 design and you no longer see this exponential decay. You start to see some plateauing of the gradients. So that's one way to reduce the expressivity of your ansatz. Another way, which I mentioned earlier in response to Will's question, was about correlating parameters. So if not all of your parameters are independent from each other, we say that your parameters are correlated. And that also reduces the expressivity of your ansatz and consequently increases gradient size. So here the red curve corresponds to uncorrelated parameters in that hardware efficient ansatz that I was showing you earlier. And then when I correlate with respect to numbers of qubits, the gradient size goes up. If I correlate that, so that's sort of corresponding, correlating vertically. If I correlate horizontally with respect to layers, then the gradient size goes up even more. And then if I correlate with respect to both qubits and layers, then I get the blue curve, which is like full correlation. and hence we get even larger gradient sizes. So it seems that there's this trade-off between, like I said, expressivity versus gradient size. And we also have some analytical results about that in this other paper. And then finally, we considered one other case of sort of reducing expressivity, and that's by restricting rotation angles of your gates. So if you restrict the sort of range of parameter values for each parameter, then you can also increase gradient size. And but this strategy only works if you initialize near the solution. So if you initialize far from the solution, then you're sort of stuck on the Barren plateau. But if you initialize close to the solution and you also restrict the rotation angles range, then you can also get large gradient sizes. Okay, so are there any questions on this? This is about sort of the connection between expressivity and gradient size. Any questions there?
Patrick?
Yeah.
On the previous slide, when you showed what happens when you start to correlate them, is that top blue line still decaying exponentially?
Yeah, that's a good question. And it looks to me like it's not, right? So I don't really, I mean, you might see an initial, like for the small numbers of qubits, an initial decay, but I don't really see for large problem sizes the exponential decay. So I think that's a good maybe observation. Granted, it's a small number of data points, but yeah, I don't see the exponential decay there. Yeah.
And sorry, how are you correlating your parameters here?
Yeah, so this is a hardware efficient ansatz, like I showed you earlier, where you have this brick-like structure and like this alternating layered structure. And there we're just, by correlating them, we just mean like we set them equal to each other. So like the parameters are tied together. And so when I say we correlate them with respect to qubits, then that means that within a layer, every parameter is the same, but they're different layer to layer. And then when we correlate them with respect to qubits and layers, then that means that basically there's just like one parameter in the whole ansatz. All the parameters are tied together. Yeah. So, okay.
Can I ask a slightly different question?
Sure, please.
Yeah, Lee Martin.
So
People often show this image of
on your video, Lee.
Yes, hi. So people often show this image of an exponentially flat region followed by a non-exponentially deep dip when they're trying to illustrate sort of the like worst case scenario Barren plateau. But it seems a little counterintuitive how you get specifically that functional form. And I was wondering sort of if you have a rough sense of what these Barren plateaus actually look like, if it's usually more just sort of a very large range of parameters over which the gradient is exponentially flat, but not necessarily some like order one very narrow dip in addition to that.
Yeah, so I tried to show a little cartoon picture earlier on a previous slide. And there it was. So this little image here. And we believe that this is actually the kind of landscapes that you get where you have basically one valley containing the global minimum, and that valley is exponentially narrow. The sort of width of the valley shrinks exponentially with the problem size. We actually gave a name to that phenomenon. We called it a narrow gorge. And so narrow gorge just means that the valley containing the global minimum is exponentially narrow.
But its depth also doesn't vanish exponentially.
What's that?
It has like a finite depth that's not vanishing exponentially.
Because, yeah, that's right. And that's because, ultimately, your cost function has some range of values, and those are, and the limits of that range are achievable. So like, meaning that, you have the ground state energy, for example, which is at the bottom, and then you have, the energy there's a concentration of there's like the top value is like the energy associated with the concentration of measure. Concentration of measure could oftentimes, for example, would be like if you're locally maximally mixed on each qubit. Like, because the idea would be, you know, say like concentration of measure means that most states are highly entangled. So if most states are highly entangled, then sort of you're like locally maximally mixed. And so the idea is that, you know, you would get like a concentration of measure effect where most of the cost values are what you would get if each qubit was like locally maximally mixed. Because then you would you're measuring local observables anyway. So all that matters is the local reduced states. And so you end up, it's almost like a sort of like kind of bipartite situation where like, you know, you have like two cost values basically, right? One is like, or that's your range. Like most cost values are around that sort of concentration of measure value, but then, you know, you also dip down, you have to dip down to the ground state energy, right? Because, you know, you do have a ground state. So yeah, this is what we find in practice. And we can also show that, we can prove that.
Okay, yeah, that makes sense, thanks.
Okay, yeah. And right. So then the next question I was gonna pose is, how do we diagnose Barren plateaus? So if you're just like an experimenter and you want to know do you have a Barren plateau? I mean, of course, you could actually make these plots, which is totally fine. You can make a plot of, you know, the variance of your partial derivative versus the number of qubits. It turns out you can do something that's maybe slightly more efficient, and that's related to the following plot. So, and this ties nicely to the previous question, which is what do the landscapes actually look like? So in the top right, I show a landscape that has both a barren plateau and a narrow gorge. The shaded region is kind of like for small problem size, and then the green one is if you have large problem size. And then on the right side, I showed the case where you have a barren plateau, where you have no barren plateau, but you have a narrow gorge. Bottom left is where you have no narrow gorge, but a barren plateau. And then bottom right is where you have no barren plateau and no narrow gorge. So you would sort of associate the bottom right with like a trainable landscape. And what you can do is you can prove that the top right and the bottom left are not possible, according, you know, like to the laws of quantum mechanics. Even though mathematically you could imagine that landscape, you can never have a barren plateau without a narrow gorge, and you can never have a narrow gorge without a barren plateau. And that's something that we proved in this archive paper. And so the only allowable landscapes are A and D, the case where you have a barren plateau and a narrow gorge, or you have neither of the two. So anyway, that's kind of like a fun fact about parameterized quantum circuits, is that the landscapes, you know, you either have both a barren plateau and a narrow gorge. Narrow gorge, like I said, means that the valley containing the global minimum shrinks exponentially with the number of qubits, or you have this sort of open landscape. So what that means is that it also means that, you know, whenever you have a narrow gorge, you also have this cost concentration effect where cost function differences are exponentially suppressed. And so what that means is that you can sample cost function differences instead of gradients to diagnose the presence of barren plateaus. And so you don't actually need to measure gradients. You can just randomly pick points on the landscape and see if those cost function differences are exponentially suppressed. So it's a little bit more efficient way to diagnose barren plateaus. And then, you know, at a deeper level, you could ask whether there's a way to predict barren plateaus based on the building blocks that you use to build your ansatz or your parameterized quantum circuit. And in this work, we considered periodic structured ansatzes like you would see in the quantum approximate optimization algorithm, where you would have, in that case, if some people are familiar with that algorithm, you have alternating layers where you have evolution under mixer Hamiltonian followed by problem Hamiltonian. Okay, good. Yeah, so there I was just talking about a simple way to diagnose Barren plateaus with cost function differences. But then on this slide, you can delve deeper into trying to understand whether you can sort of engineer away Barren plateaus based on your ansatz design. And in this work, we considered ansatzes that had a periodic structure, like you would see in the quantum approximate optimization algorithm. In that case, which some of you are familiar with, you have a sort of back and forth situation where you evolve under a mixer Hamiltonian, followed by a problem Hamiltonian, followed by mixer, problem, mixer, problem. And so the ansatz has a periodic structure. And then you can look at the Hamiltonian generators that appear up in the exponential for that ansatz. And then you can compute something called the dynamical Lie algebra, which is formed via the nested commutators of the Hamiltonian terms in that ansatz. And what we found is that there appears to be a connection between the dimension of that dynamical Lie algebra and the gradient sizes, that is whether you see Barren plateaus or not. So here is a numerical plot of the variance of the partial derivative of the cost function versus 1 on the dimension of G. G is the dynamical Lie algebra. And we found that, excuse me, as you grow, let me just drink some water. As you grow the dimension of the dynamical Lie algebra, then the gradient sizes get smaller and smaller. And so, there's certain classes of situations. This is language from quantum optimal control. If your ansatz is controllable, where and hence G is full rank, then we find that you always will hit a Barren plateau. So the idea is that you want to avoid the situation where your dynamical Lie algebra is sort of large in size. And so anyway, this was interesting because it made us realize that even when you have something called a problem-inspired ansatz, where your ansatz is inspired by the Hamiltonian of your problem that you're trying to find the ground state for, you can still run into Barren plateaus, even for problem-inspired ansatzes. And hence, just because you have a problem-inspired ansatz like you would have in the quantum approximate optimization algorithm, doesn't mean you avoid Barren plateaus. And so there appears to be a connection in these ansatzes between something like an algebraic property and gradient sizes. And so that's interesting. This is just the sort of first work on this problem, and I think there's more to be done here. But it suggests that there may be an algebraic theory lurking in for Barren plateaus. So the next question we asked was, can we extend the Barren plateau result to shallow depth? So up to now, I've been talking about deep circuits and how Barren plateaus arise whenever you form a 2 design. But there's an interesting question as to whether you can see this phenomenon for shallow circuits. And it turns out the answer is yes, if you allow the phenomenon to depend on the cost function. So we had this paper called Cost Function Dependent Barren Plateaus in Shallow Quantum Neural Networks. And there, once again, we consider the same ansatz that I showed you before, where you have this brick-like structure. It's called the hardware efficient ansatz. And we assumed that each individual block formed a local 2 design, and we considered 2 different types of cost functions. One in which you have, say, a global cost function, and the other in which you have a local cost function. Now, local cost functions are what you would typically expect from physical Hamiltonians. Like, for example, if you want to find the ground state of a condensed matter system, you're going to have a local Hamiltonian here. Global cost functions arise whenever you, for example, are trying to find like the fidelity with a target state. So it's like, imagine that your goal is to prepare a certain state, and you decided to use a cost function which is like the overlap your state with that target state. That's what we would call a global cost function, because you're making a global comparison between your quantum state and some other state. So what you can show is that global cost functions face serious problems. Namely, the variance of the partial derivative vanishes exponentially, even if the depth is shallow, like the depth is, say, polylog n or even less. Sorry, excuse me. And then the local cost functions are at worst polynomially decreasing as long as the circuit depth is log n. And so what this looks like when I show it on like in picture form is that whenever you have for global cost functions, when the circuit depth is order 1, like constant or log n or polylog n, then you have an exponentially vanishing partial derivative. Whereas for local cost functions, we have a region of sort of trainability, where whenever the circuit depth is log n or constant, then we have only polynomially vanishing gradients. So we don't have Barren plateaus. And if we combine this with the Google result, which is for polynomial depth circuits, then we find that global cost functions basically have Barren plateaus essentially for all circuit depths that we studied here. And whereas local cost functions have Barren plateaus for deep circuits, but not for shallow depth. And that's an interesting phenomenon that you can sort of see in this numerical implementation. We took a case of a quantum autoencoder. A quantum autoencoder is a type of variational algorithm where you're trying to basically shrink the number of qubits in your system. This is very much analogous to classical autoencoders. It's considered a data compression technique. And there we can plot the cost function versus number of iterations, the training curves for different numbers of qubits. So we consider 10 qubits, 15, 20, 25, 30, all the way up to 100 qubits. And we can show you curves for training a global cost function, which is the red curve, versus training a local cost function, which is the blue curve. And for the local cost function, we found trainability all the way up to 100 qubits. But for the global cost function, which once again, like I said, you can think of a global cost function as being like a fidelity-based cost function where you look at the overlap with the target state. The global cost function trains well for 10 qubits, 15 qubits, but then once you hit 20 qubits and 25 qubits, it starts to become untrainable. And beyond 25 qubits, it's just a flat line and it's completely untrainable. And so this shows you the impact of Barren plateaus. And it also shows you that you can be fooled sometimes by trainability at small problem sizes. So you might be fooled if you just train for 10 qubits, you might be fooled into thinking that you didn't have a Barren plateau. But then once you hit 20, 25 qubits, the impact of the Barren plateau really becomes obvious here. So in a practical situation, the impact of this result has been sort of elaborated on by this Russian group, Uvarov et al. And they looked at fermion to qubit mappings in VQE. So they were solving a condensed matter ground state problem. And they looked at, so whenever you solve a fermionic problem, you have to first map it to qubits. And so there's a fermion to qubit mapping, for example, the Jordan-Wigner transformation or the Bravyi-Kitaev transformation. And you could ask, like, which transformation is actually better for trainability? And it turns out that it's known that the Jordan-Wigner transformation leads to non-local or global terms in your Hamiltonian, like polystrings that involve non-trivial poly operators on every term. And sure enough, they found that the Jordan-Wigner transformation had Barren plateaus for shallow depth. So, and it was just very interesting because, it's known that the Jordan-Wigner transformation generates global terms in your Hamiltonian, in your poly Hamiltonian. And so, and sure enough, that translated into shallow depth Barren plateaus. Now for the Bravyi-Kitaev transformation, it's known that it leads to more local terms. And so you tend to get local terms in your Hamiltonian after the transformation. And sure enough, they found that they avoided this shallow depth Barren plateau. Yeah, so that's this sort of shallow depth Barren plateau issue. Are there any questions on that?
Patrick, I had a question a few slides ago. So it's on where you described the Barren plateau for the global cost function.
Mm-hmm.
So you said that you can look at this global cost function as some overlap between your output state from your quantum neural network and your target state. But what happens when your target state can now be prepared with some log and depth circuit? Do you still get a Barren plateau in this case?
When your target state cannot be prepared with
can be prepared with a long end circuit.
When your target state can be prepared with the shallow circuit.
Yeah.
Yeah. Even then, you still get this phenomenon. So you can see this phenomenon even just for preparing tensor product states. So, with a depth one circuit. So imagine that your target state is a tensor product state. And then you try to prepare that tensor product state. When you compute their fidelity, it's just the product of their local overlaps. And if each local overlap is less than 1, then you basically have a product of numbers that are less than 1, and hence you have something that's exponentially getting suppressed. And so, then even for this super simple example where you have a depth 1 circuit for both your ansatz and for your target state, you can still see this Barren plateau phenomenon.
What if, so I'm assuming you mean like the 0,0,0,0 state on every qubit. Sure. What if instead you prepared some state which is like the maximally mixed state on n-1 qubits, and it's non-trivial poly on a single qubit? Now it looks local. So that type of state prepared with some log n circuit, can you avoid a Barren plateau in this case?
Oh, you're talking about a mixed, you want to prepare a mixed state?
Yeah.
Okay. You want, like, your goal is to prepare a mixed state, or
your goal is your target state, just for the sake of you avoiding a Barren plateau, your target state is some mixed state evolved with some log n circuit. And I want to learn that particular state just for the sake of seeing if I can avoid a Barren plateau.
I'm not sure. I mean, usually we consider, in all of our proofs, we've always considered pure state preparations. So I don't have a proof to answer your question. It's an interesting question. More often than not, Barren plateaus are usually harder to avoid than they are. It's hard to avoid Barren plateaus. So, the initial intuition would be might still be an issue, but I don't have an answer. Maybe we should continue that conversation via email. I think it'd be an interesting conversation to have. Yeah. So thanks for the good question. So that's the situation with local versus global cost functions. I realize I'm sort of running out of time. And so the last thing I just want to mention is that, everything I've talked to you about thus far, we have a solution for. Like Barren, expressibility induced Barren plateaus can be avoided by just reducing expressibility. Cost function induced Barren plateaus can be avoided by changing the cost function from global to local. But now I'm going to talk about a problem that we might not have a solution for yet, or a satisfactory solution. And it'll just take a minute or two, but it's called noise-induced Barren plateaus. And we consider this situation where you have, you have local noise acting on each individual qubit after each, layer of your ansatz. And what we found out is that the partial derivative is exponentially vanishing with the number of qubits whenever the circuit depth grows polynomially in the number of qubits. And it's a different kind of phenomenon than what I've talked to you about earlier, because you no longer get this kind of narrow gorge phenomenon. The landscapes just concentrate about a fixed value, and you get a situation like this on the right, where as I increase the number of qubits, the whole landscape is concentrating about a particular value, and namely that value is the value associated with the fixed point of the noise model. And you can understand this from the fact that the state itself is actually approaching the fixed point of the noise model. So your density matrix, for example, if you have a depolarizing noise model, your density matrix would be approaching the maximum mixed state. And it's approaching that as you increase the circuit depth. But if you have the circuit depth grow polynomially in the problem size, then it'll approach that as you grow the problem size too. And so this is a big issue because both the variational quantum eigensolver for finding ground states and the quantum approximate optimization algorithm, both of those algorithms propose to use ansatzes that grow polynomially in the number of qubits, where the circuit depth grows polynomially in the number of qubits. And so, and just to show you the impact of this for the quantum approximate optimization algorithm, without noise, you might think that you have quantum advantage, whereas with noise, it turns out you can destroy quantum advantage. And so the blue dashed line here is the state-of-the-art classical algorithm for solving this combinatorial optimization problem known as max cut. And this algorithm is called Gomans-Williamson. And so without noise, you have this black curve, which is the performance of QAOA on the max cut problem. And so it looks like you're above the classical threshold, like it looks like you're achieving quantum advantage. But then once I put in noise, so I just have noisy training, the noise actually hinders the training process because the landscape gets flatter and flatter. Even if I have noise-free final cost evaluation, as I increase the number of qubits, you can see that I dip below the blue line. And so it looks like noise can actually destroy quantum advantage in these QAOA problems. And so this noise-induced Barren plateaus is actually arguably the most important issue that we have for this paradigm of variational quantum algorithms. And you might ask, well, can error mitigation solve noise-induced Barren plateaus? There's this whole field of quantum error mitigation. For example, people have proposed to use zero noise extrapolation, where you just vary the noise level in your circuit and then you extrapolate your observables back to the zero noise level. These error mitigation methods can be thought of as classical post-processing of data obtained from different kinds of circuit runs. And so they're kind of inherently classical in their nature. It turns out that the answer is no. We have another paper showing that you still get exponential scaling of resources even if you do error mitigation. And the intuition behind that is that error mitigation can definitely boost up your gradients, but it also boosts up your shot noise. And so it increases sort of the variance of your observables. And it does so kind of proportionally. So if it bumps up your gradients, it'll sort of bump up your shot noise by the same amount. And ultimately, trainability is about the relative values of the gradients to your shot noise. Because if you had infinite precision, Barren plateaus would not be a problem because you could still navigate through that landscape. But whenever your shot noise becomes comparable to your gradient size, then you can't decide where to go in your landscape because you can't discern between signal and noise. And so error mitigation does not appear to solve this problem. Most recently, just in the past month, we had a paper looking at the question of whether error correction could solve the noise-induced Barren plateau problem. And we introduced some very simple toy model for a situation in which you have partial error correction, like a subset of your qubits are error corrected, and the other set of your qubits are just dirty qubits. And that simple model, we call it the clean and dirty model, where your error corrected qubits were just noiseless. They just had no noise on them. It's a very simple model, but we just wanted to understand whether in principle, you could actually avoid noise-induced Barren plateaus with error correction. And it turns out that this plot on the right-hand side shows the gradient versus the number of layers. And we do see exponential decay in all cases, even whenever a subset of your qubits are error corrected, but the exponent is basically proportional to the ratio of the number of dirty qubits to the total number of qubits. Or in other words, each clean qubit that you add exponentially increases the gradient size. So you can see as I go up here to different curves, I'm adding more clean qubits, and hence so I'm increasing the gradient size here. So it does look promising that you can exponentially increase gradient size if you can error correct a subset of your qubits. Okay, so that's the end of my talk. Sorry for going over time a little bit, but just to conclude, Barren plateaus are one of the few complexity theoretic results that we have for these variational algorithms. They can determine whether or not quantum speedup is possible, and they're connected to expressibility, controllability, locality, and noise. And certainly strategies to avoid them is a crucial area of research. So thank you very much for your time and good questions.
Well, thank you very much, Patrick, for a wonderful overview of this subject. I think this should generate a great deal of discussion, and we have a little time, even though we're a bit over time. So please turn on your video so we can see the people here and who wants to have the first question.
Yeah, I know people have asked a bunch of questions already throughout the talk.
Roy and Lee asked several questions already, but Roy is.
I have another, but I want to give someone else a chance.
Hi, Feng, you have a question?
Yeah. So hi, Patrick. This is a very nice talk, and in your slides you quantify the expressivity by the TT design, right?
Sorry, you said quantify expressibility?
Yeah, using the T design of the unitary ensemble. Yeah, but in traditional machine learning, people use the VC dimension or random complexity to quantify the expressivity of the ansatz of the hypothesis. So is there any connection between the expressivity you mentioned here and the VC dimension or the random complexity?
That's a great question. Yeah, I mean, the expressibility measure that we used, as you can imagine, was nicely mathematically connected to sort of this Barren plateau phenomenon, because it was looking at basically how far away you are from a two design. Our group has not actually looked at this, but I think the IBM group has looked at this. They have this paper called "The Power of Quantum Neural Networks," and they introduced a different measure called the effective dimension, but I think it was kind of similar in spirit to the measures that you were talking about. And then they found a connection between effective dimension and gradient size. But so they do have a result there. But I haven't seen a paper that looks at Rademacher complexity or VC dimension, and I think that would be interesting. Yeah, it's still a very young field, so there's definitely room to explore that. We've connected these measures of complexity to generalization properties of quantum neural networks. So I have a paper with Robert Huang and Matthias Caro, and there we have a measure of complexity similar to that you mentioned. And we connected that to how well your quantum neural network generalizes on unseen training data, but we haven't connected it yet to gradient size. So it's a good question. Yeah.
Okay, thank you.
So Roy, did you have another question?
I did. So Patrick, in your cost function dependent Barren plateaus paper, I think you always throw in the 000 state as your input state. Is that right? So now what happens if you start wondering, what if my training data, is not just a 000 state? What kind of training data can I throw into my, hardware efficient ansatz so that I can still train it? Do I get a Barren plateau if, my input state is too general?
Yeah, so we might have actually gone beyond the all zero state. It's been a while since I've looked at that paper, but I'm pretty sure we considered, possibly having mixed state inputs, but you end up with a term that looks at how close your reduced density matrices are to being maximally mixed. There's another source of untrainability, which is like, if you had, if you're acting with local gates on each individual qubit, but then locally you're maximally mixed, then that's untrainable because you can't train a maximally mixed state. You can't, because obviously it's invariant under unitary rotations. And so what we ended up with the term in the bound, which is like the Hilbert-Schmidt distance between the local reduced state and the maximally mixed state. So implicitly in our bounds, we were kind of assuming that term wasn't like exponentially small or something, right? That you weren't like exponentially close to, otherwise our trainability guarantees would have been, null and void. But so you can run into another issue, which sometimes people call entanglement induced Barren plateaus. Actually, there's a group, in Toronto, Nathan Weeb, and they had a paper called Entanglement Induced Barren Plateaus. And it was especially about this thing, which is like, what if you fed in to your quantum neural network? What if you fed in a state that was really highly entangled? Then you would just kind of get untrainability from the get-go, like regardless of, And so you can imagine also, this is important in the context of quantum machine learning for like embeddings. So if you have, in quantum machine learning, oftentimes what you do is you first do what's called an embedding, where you embed your data in the Hilbert space, and then you act with a quantum neural network on that embedded quantum state. But what if you embed into highly entangled states, right? So you have like your data coming in, and then you embed it, and your embedded state is so highly entangled that it's like sort of locally maximally mixed. Then your quantum neural network will be untrainable. And so, so that's what people sometimes call entanglement-induced Barren plateaus. And so it's, anyway, I don't know if that answers your question. But yeah, that's another mechanism. So in our bounds, I guess, like whenever we say we have trainability, we were assuming that your input state was kind of well behaved, right? Like, and it doesn't have to be the all zero state, but it does have to be well behaved. It has to be like not exponentially close to being maximally mixed on each qubit. Yeah.
So one follow-up question. So you guys also have this result on, Barren plateaus when you try to learn some R-random unitary, and this R-random unitary typically maps you to some maximally mixed state or something very close. So wouldn't your result also imply that if I threw in some R-random input, which would presumably be very close to maximally mixed, I should get the same issue? So is this another way of looking at this? I can't learn a random unitary. It's the same problem as I can't throw in a random state. Are these the same problem?
Yeah, so we had a paper called Barren Plateaus Precludes Learning Scramblers. I think you also had some recent work on this. I think Arthur had a paper related to learning scrambling unitaries. But yeah, there seems to be a duality, like you're saying, between trying to learn unitaries from a set, like if the set of unitaries that you're trying to learn is kind of too broad, then you can run into a Barren plateau there. It's kind of a different mechanism, but at the same time, it's like a duality, I guess, like a state slash map state duality. But anyway, yeah, so you can run into a Barren plateau whenever, like if the set of unitaries that your unitary is drawn from, the unitary that you're trying to learn, if that set of unitaries forms a two design, then I think you hit a Barren plateau there, which is a different mechanism. So it's kind of cool.
But you could also just look at this as this unitary that you're sampling from can be used to prepare some input state.
Mm.
And
yeah, that's true.
So I mean,
Yeah.
it's a different learning problem. One is about training with input states. One is about learning a particular target, but the cause function is
Yeah.
basically the same.
Yeah, in that paper that we had, what was kind of cool about it is that the Barren Plateau happened regardless of what your ansatz was. So it was like ansatz independent. It just depended on like the set of unitaries that your target unitary was drawn from. And so it was, that's why it felt like a different mechanism, because it was ansatz independent. Yeah, anyway, sorry. Yeah, I think I agree with what you're saying.
All right, thank you for all the answers.
Yeah, no problem.
So does anybody else have a comment?
So Patrick, to avoid the Barren 2, what kind of like data embedding we could use?
What kind of what?
Data
Like, yeah, data embedding.
Data embedding?
Yeah.
Like in the context of quantum machine learning?
Yeah.
That's still an open question as far as I know. And it's not obvious. I mean, there's a popular embedding that people use. I think it's called like IQP embedding, but it's not obvious that avoids Barren plateaus. I think that we've started to learn about Barren plateaus in the context of variational quantum algorithms, and quantum machine learning is even newer than variational quantum algorithms, and so we know even less about QML, Barren plateaus in QML, than we do in variational algorithms. And and the embedding is like a novel thing, right? We don't really have embeddings in variational algorithms, but we do have them in quantum machine learning. And so like, that's all, I think there's a lot to be studied there in terms of what embeddings avoid Barren plateaus. I mean, at the very least, you have to avoid embedding into highly entangled states, for what I was just talking to Roy about. Yeah, so you have to embed into states that are not like hard random states or states that are highly entangled, so that you have local trainability, because you're going to feed this right into locally parameterized quantum neural networks. So it has to have local trainability. And so it can't be locally maximally mixed. That's the intuition, right? But actually designing that is another question.
Okay, I see. But if you think about the state embedding as a quantum feature map, so like what kind of feature map? Oh, I think the kernel method is related to the feature map. So is there any connection between in the kernel method, we always care about the spectrum of the kernel matrix. So is the gradient of the training is related to the spectrum of the kernel matrix?
I'm not sure. I don't know. But yeah, you're right that this is connected to kernel methods, because kernel methods have that feature map. But I don't know. Maybe we can keep that conversation. We can talk about that over email. And yeah, that would be an interesting question.
So Patrick, I think that this is a really interesting conversation, and it can continue for quite a while. So maybe some point in the near future, you could visit us in Cambridge, and then we could have a pretty intense conversation that way. It would be great. And in the meantime, we really thank you for the interesting talk and covering so many different topics and explaining them so nicely.
Great. Yeah, thanks for the great questions as well. It was really good.
So we're now going to take a pause in our seminar for, as I mentioned at the beginning, and we June 20th to 23rd have an interesting set of lectures in person here in Cambridge. And then sometime toward the end of the summer, we'll start the online seminar again. So thank you very much, Patrick. Thank you for all the visitors and viewers, and we look forward to seeing you soon online or in person. Bye-bye.
Sounds good. Thank you so much.
Thank you.
Bye-bye.
Thank you.